continue. This is continuation of last exercise. So we have defined the Newton number for dimension 1. Find mod over K0. Of course, we should define it for general. So definition: if D is a phi n module over K0 of dimension h, such that again Frobenius is bijective. If you look at the definition of phi n module, we don't require this Frobenius to be continuous. Then let E1, E2, EH be any fixed basis of D over K0 such that phi of EI be described by this matrix A. Okay. And then, of course, we are going to define this Newton number using this matrix. So you see that this Newton number is tell you more delicate information about this Frobenius, right? So we're going to define this to be again the p-adic evaluation, but this time over the determinant of A. Second thing, I'm going to define alternative definition. So the exercise would be firstly check this definition is well defined as the last exercise. Secondly, check the alternative definition is equivalent. Again, if D is a phi n module over K0 of dimension h such that Frobenius is bijective, over D, then we set Tn of D to be Tn acting on the one-dimensional Q vector space wedge HD. Okay. So let's first check, let's say definition 1, definition 2. Definition 1 is well defined. Second exercise, check definition 1 and 2 are equivalent, are the same. Okay, solution. So let there be another basis. So this is just linear algebra for D over K0. Then we write this Frobenius over this EI prime using, again, let's say AIJ prime. with EK equals, so there is transition matrix. I'm following lecture notes from the internet on the elegant program master thesis. And transition matrix. Conversely, then we set matrix P to be this. Transition matrix, matrix A prime, EIJ prime. This is frobenius with respect to another basis. And set Q the transition matrix reversed to position the two bases. Then obviously they inverse each other in the matrix because you start with this basis, you got another, and vice versa. Now let's compare. Compare what? Compare on the one hand we have the determinant of A, where A is the matrix when we use the first basis. On the other hand, we should have another basis, A prime, and we have to look at that matrix with respect to that basis. How to find the relation? So that's the following computation. Firstly, we write frobenius of EK. This is, it has a relation with EI prime, and then by semilinearity, I could separate this phi EI prime, and then could continue. And we continue. Sigma EI prime could be written as EIJ prime. Oh yeah. And finally, express this as a matrix. Sigma P, A prime, Q, so what we have is, so this is again just express EK using EK. Sorry, so there is no longer I. just double sum k and let me think k and l. Yeah, there is no k basically because k is fixed, so this is actually L. Sorry for that. So finally we k and L. And so we have two different expressions. The first here is just A, and the second is here, and this is for fixed basis, so this is telling us we have this relation, with no surprise, and therefore the determinant of A should be the determinant of the sigma p, a prime, q, and then we call determinant of this is just determinant of each one. Okay, replace q with p inverse, so prime determinant of p inverse. So this is just finally Vp of determinant of sigma p plus Vp of determinant of a prime. This gives us a way to compare the prime determinant of a with determinant of a prime, and minus determinant of minus Vp of determinant of p. So finally, what's the difference between the two valuation determinant and their different bases? They're different by I don't really need to separate it, but fine. It's just determinant sigma p over p. And so it's also just sigma of determinant of p over determinant of p. Just notice this determinant of p lies in K0. And so for similar reason, this is just 0 as last exercise. So sigma of determinant p is determinant sigma p because sigma is this time is just ring homomorphism, and so this is just a polynomial, and so it could move it out, and so we have proved what we want. Second part of the exercise, let's show the second alternative definition is equivalent. So recall that we're setting D is phi n So let's see, recall D is phi n module with dimension h. And then the trick is we'll construct a one-dimensional QZ vector space where there arise naturally this determinant of this AI. How did that happen? Notice phi is bijective over D implies phi is also bijective over this wedge of D. And if E1 is a fixed basis of D, then E1 wedge till En is a basis for this one-dimensional vector space. And now we're writing phi VI, suppose it is AIJ. Then I can set A to be the AIJ, and we will have phi of E1 wedge E2 En equals determinant of A times E1 wedge EH. This is from the, so the Frobenius on the wedges, again, just component-wise the Frobenius, but by the formula you have this summation of AIJ and the property of alternating, something like that. The property of this wedge finally tells you that here it is just determinant of A. And therefore, by the definition of Newton number for one-dimensional QZ vector space, this TNO, which is just by our last exercise, determinant of A with P, which coincides with the definition today. Okay, so